So this is section 4.4, the law of sines, and we are going to continue on with solving triangles. And specific cases, or what I mean by the cases is when you're given certain information about triangles, we're going to be solving those different cases using something called the law of sines. So we've already talked in previous classes, you guys have solved for right triangles using SOHCAHTOA. Remember, right triangles have an angle that is equal to 90 degrees. And now we're going to be looking at solving oblique triangles. So acute triangles where all three angles are less than 90 degrees, and obtuse triangles where one of the angles is greater than 90 degrees. This is going to be our labeling technique for our triangles, and we're staying consistent with our textbook. Different textbooks might use different labeling, but this is what we're going to use. So the side opposite the angle alpha will be lowercase a, the side opposite the angle beta will be lowercase b, and the side opposite gamma will be lowercase c. So we've already solved right triangles using SOHCAHTOA. So we've solved for the unknown sides and angles using given information and then SOHCAHTOA. Now we're looking at solving oblique triangles, and there are 4 different cases. Now you always have to know at least the length of one of the sides, and then either 2 angles or another angle in another side, or the other 2 sides. So we've split these into 4 cases. Now case 1 and case 2 are what we're solving in this section using law of sines. And case 1 is when you have 2 angles in a side, so that would either be the angle side or the angle side angle. And then case 2 is something that we refer to as the ambiguous case, and you have to watch out for it. We'll talk about how this ambiguous case can occur, but that's when you have 2 sides in an angle. So as the SSA case, or to remember it, you can always think of it as the ASS case. And that just lets you know that you need to watch out for that case. Okay, case 3 and case 4, we're actually going to be looking at in section 4.5, where we're using the law of cosines to solve these cases. Oops. And then just a note on here that remember there can't be an AAA case because there would be, so if you knew all 3 angles of a triangle, remember there are infinitely many triangles that could fit that set of 3 angles, right? That's by definition similar triangles. So this is the law of sines. And so the law of sines is if you have the sine of alpha over the sine of alpha over its opposite side A is equal to the ratio of sine of beta over side B, which is also equal to the ratio of sine of gamma over side C. And this can also be flipped, the reciprocal, depending on what you're solving for. You might want to use either version of the law of sines. So this can also be written as A over sine of alpha equals to B over sine of beta equals to C over sine of gamma. And then just a note on here, the longest side of a triangle is opposite the largest angle, and the shortest side of a triangle is always opposite the smallest angle, and that will be helpful to us going forward. So it depends on what you're solving for. So if I were solving for an angle, I would probably want to use the first law of sines up here. In order, it would just be less steps. But if I were solving for a side, I would probably use the second version of law of sines here, where the side lengths are in the numerator. Okay, so let's look at our first case. So this is case 1, and is the AAS case, and that's because we have an angle, and a side for what we're given. And so we need to solve for the angle gamma and then the side C and side A. Now, when you are solving for these unknown sides and angles, you need to represent them exactly before you write your approximation. And if you also need to use exact values when you are solving for another unknown. So in order to do this, it's going to be helpful for you on your calculator to use the store function. So where you can store values and call them back up. And I made another little video showing you how to do that, but I'll also describe it as we go through these problems. And not all the problems we'll have to do. We won't have to do that for all of the problems. Okay, so why don't we solve for angle gamma first? I'm just looking at, we could solve for side A, but it might be more efficient to start with just solving for angle gamma, so we have all three angles. So gamma equals, remember all three angles sum to 180 degrees. So gamma would be equal to 180 degrees minus the sum of those two angles. So minus 105 degrees plus 43 degrees. Don't forget to have your degree symbols. Very important. If you don't have degrees, it indicates that the angle is in radians. So the angle gamma ends up being equal to 32 degrees. Okay. Next, we could solve for side A. Although since we know what gamma is, we could also solve for side C, but we'll just go in alphabetical order. So using law of sine, since I'm solving for the side length A, I'm going to do A in the numerator here over sine of 105 degrees equals, and I like to use the given information as much as possible, although we don't know what C is, so we couldn't use C. So that would be equals to B, which is 30 feet over sine of 43 degrees. So to get A by itself, we will multiply by sine of 105 degrees on each side. So A is equal to 30 times sine of 105 degrees over sine of 43 degrees. So that's the exact value. You need to type that into your calculator to get the approximation. And when we do that, we get 42.490, and there's units on this one, so feet. So that's the approximation. That would be the exact value. And then to finish solving this triangle, we need to solve for side C. We don't need to store the value of A since we can use the given information of side B and the angle beta. So we're solving for C. So C over sine of 32 degrees equals to 30 over sine of 43 degrees. So C equals to 30 times sine of 32 degrees over sine of 43 degrees. So that's the exact value. Type that entire ratio into your calculator. Make sure you are in degrees, in degree mode. So hit the mode button and make sure you're in degrees. Since our angles, our inputs are in degrees. And we get C is approximately 23.310 feet. So that's the approximation That's the exact value. Okay, still case 1, but angle side angle for what's given. I would again, here, let's just switch colors. I would again just solve for that third angle first. So alpha would be 180 degrees minus the sum of the other two angles. So alpha equals to 35 degrees. And then I'm going to solve for side B. So B over sine of 85 degrees equals, again, I like to use the given as much as possible. So we would have to use the fact that A is equal to 12 inches over sine of 35 degrees. So B equals to 12 times sine of 85 degrees divided by sine of 35 degrees. That's the exact value. And when we type that into the calculator, the approximation we get is 20.842 inches. So our approximation and our exact value. Okay, and then to solve for side C, I'm going to put C in the numerator over sine of 60 degrees equals to 12 over sine of 35 degrees again. So C, I'm going to move this over. C equals to 12 times sine of 60 degrees over sine of 35 degrees. That's the exact value. And then typing that into your calculator, the approximation is 18.118 inches. So the approximation and the exact value. So we're going to look at case 2 next, the ambiguous case. So for the ambiguous case, I'm going to switch to black here actually. That means that you're given an angle and two sides. So let's say that the given is the angle alpha and then sides A and B. Okay, and let's say that alpha is acute. Okay, so I'm just going to show you how you can run into the 1, 2, or 0 triangles with this given information. So let's say that this is alpha, okay, this is side B, and this right here would be the height of the triangle. Side C would be over here. Now, if side A, so the given side A is less than the height of the triangle, which you could solve for the height of the triangle since that creates a right triangle, right? And you know alpha and you know side B, you could figure out what the height is. So if side A is less or shorter than the height of the triangle, think about that. Then side A would just kind of like hang here and it wouldn't be able to touch side C. So in that case, there's no triangle. Now, if, I'm going to try and draw that same picture. So if we have alpha B, now if the height inside A are equal to each other, then there's one triangle. And that triangle would actually be a right triangle. Right? This would be, A would be equal to H. And that forms a right triangle. Now, if A is greater than the height, but shorter than side B, that's whenever you can end up with two triangles. Let me do my best to draw this. So we would have alpha, this would be side B. This would be the height. So if side A were shorter than side B, but greater than the height, then there could be two triangles. So I'm going to draw this in blue. You could create the triangle here, right? That's a possible side A. Or if you swung it in, that's a possible side A. So that's when you run into two triangles. And if side A is greater than or equal to side B, then there's one triangle. So if side A is longer than side B, or greater than or equal to, I should say, then there's one triangle. Okay, now if alpha is obtuse, there's only one triangle. It's if alpha is acute, so if the given angle is acute, that's when there's possibly two triangles. My suggestion would just be, if you recognize you have the SSA case, try and solve for a second triangle, and that's what we're gonna do in our examples. Okay, so we're gonna solve this triangle where we're given alpha is 133 degrees, A is equal to 48 meters, and C is equal to 17 meters. Now, we know from what I just said that there's only one triangle that's possible here because the given angle is obtuse. However, I'm going to show you what happens if we try and solve for a second triangle. Now, often when I'm not given a picture, I like to just draw a sketch of a triangle and label, right? So I know that I'm given alpha is 133 degrees, side A is 48 meters, and then side C is 17 meters, especially if I'm trying to visualize what case I'm dealing with the given information or what I can solve for. Okay, so we have to solve for angle gamma first. Like, that's the only option to solve for first. So we're going to have sine of gamma over 17 equals to sine of 133 degrees over 48. And forget sine of gamma by itself. That's 48. And then gamma would be equal to the inverse sine of that ratio. Okay, that would be the exact value of gamma. And if I type that into my calculator, I get gamma is approximately 15.012 degrees. Now, sine is positive in quadrant 1 and quadrant 2. Okay, right? The values of sine positive in quadrant 1, quadrant 2. Think about your unit circle where the y coordinates would be positive. Quadrant 1, quadrant 2. So that means angles between 0 and 180 degrees have positive values for sine. And if you think about the unit circle, right, aren't those ratios like reflected in the angles reflected over the y-axis? For example, sine of 30 degrees is equal to 1/2, and so is sine of 150 degrees. Well, 180 minus 150 degrees is equal to 30 degrees, right? So there are two angles that would make this a true statement, is what I'm trying to say. Inverse sine is going to give you the angle from quadrant 1 every time. So if we want to figure out what the angle from quadrant 2 is that would make that a true statement, we can subtract from 180 degrees the angle that we just came up with. So I'm going to treat this as gamma sub 1. So like gamma from triangle 1. Like pretend that there are two triangles that exist with this given information. So then if I go and try and solve for triangle 2, gamma sub 2, which would be gamma from the second triangle, would be 180 degrees minus that gamma from the first triangle. And here's where you would want to store into your calculator. So you hit the stove button, or you've already typed in inverse sine of 17 of sine of 133 degrees over 48, hit enter, and you have the approximation in your calculator. You then hit the stow button, and then you hit the green alpha button. Pick a letter that you're going to store that under. So whether you want to store it under C, right, for gamma, or under A. And you just pick a letter, and you might want to make a note on your page of what you're storing it under. So that then, in order to represent the exact value of gamma from the second triangle, right, this would actually represent gamma from the second triangle, like the exact value. And then if you type that into your calculator, 180 degrees minus whatever you stored gamma sub 1 in as, you'll get approximately 164.988 degrees. Now here's why you don't need to worry about there being a second triangle when you're given an obtuse angle for the triangle. Is 164.988 degrees plus 133 degrees. Well, that's greater than 180 degrees. Therefore, that's not a possible triangle. So let me write this down. So because alpha, the given alpha plus gamma sub 2 is greater than 180 degrees, there is only one triangle. It does not make sense to have a second triangle with an angle of 164.988 degrees. So we can continue on. I'm going to erase that sub 1. We can kind of ignore that second triangle that we tried solving for, and we can go ahead and solve for, how about, well, we could solve for beta, the last angle. So beta would be 180 degrees minus 133 degrees plus gamma. And it's good you've already stored gamma in your calculator. Now you can just type in 180 degrees minus 133 degrees plus whatever letter you stored gamma under. And when you hit enter, you get that beta is approximately 31.988 degrees. Store that value, okay? Because now we need to solve for side B. So side B over sine of beta, and when you type beta into your calculator, you're using whatever letter you stored beta under. But everything on our page represents exact values. So B would be equal to 48 times sine of beta over sine of 133 degrees. That represents the exact value of B. Type everything into the calculator using your stored value for beta, and we get B is approximately 34.768 meters. And then just make sure that it's very clear what your final answers are. So, like, we have our value. I'm just going to highlight the approximations actually. Okay, so we solved for all 3 pieces of information that we were missing here. Okay, so now let's go ahead and solve this triangle. We're still in the ASS case. Again, I like to draw just a picture of a triangle and label what I'm given. So alpha is 72 degrees. A is 8.1 meters. B is 8.3 meters. B, oh wait, no, that's, whoopsies. B is 8.3 meters. That's beta, gamma, C. Okay. So what do we have to solve for first? It looks like angle beta we would need to solve for first. So sine of beta over 8.3 equals to sine of 72 degrees over 8.1. Sine of beta equals to 8.3 times sine of 72 degrees over 8.1. So beta would be equal to inverse sine of 8.3 times sine of 72 degrees over 8.1. Remember, this is just one of the solutions for beta, right? If we think about this equation here, there's an angle from quadrant 1 that would make that a true statement, and an angle from quadrant 2. So if you type that into your calculator, you'll see that beta is approximately 77.043, which, remember, inverse sine of that positive ratio is always going to be an angle from quadrant 1. We're going to treat that as beta sub 1. So like beta for triangle 1, and pretend there's, okay, now a second triangle. Here, I'll even switch colors. So let's start solving for triangle 2 by solving for beta sub 2. That would be beta from the second triangle. So that's 180 degrees minus beta sub 1 which is approximately 102.957 degrees. And remember, you have stored beta sub 1 in your calculator. Okay, so let's solve for the third angle. So gamma from triangle 2 would be 180 degrees minus the sum of 72 degrees and beta sub 2. And you've stored beta sub 2 in your in your calculator so that you can type in just the letter in your calculator for beta sub 2. And we get approximately 5.043 degrees. So small angle, but because we did end up with that third angle, there's two triangles that exist from this given information. Okay, so let's go back to triangle 1 and solve for gamma in triangle 1. So gamma sub 1 would be 180 degrees minus 72 degrees plus beta sub 1, and you still have beta sub 1 stored in your calculator. It can be really helpful to make notes on your page about what you're storing the values in your calculator. So that ends up being approximately 30.957 degrees. Okay, so for both triangles that exist here, we're missing side C. And I'm going to give myself an extra page. Okay, so solving for side C with triangle 1, I'll have C sub 1 over sine of gamma sub 1. And I've stored gamma sub 1 in my calculator. Equals to 8.1 over sine of 72 degrees. So C sub 1 equals to 8.1 times sine of gamma sub 1 over sine of 72 degrees. So that's the exact value. Type that into your calculator. And it's approximately 4.381 meters. Switching back over to green from triangle 2, C sub 2, so side C from triangle 2, would be C sub 2 over sine of gamma sub 2 equals to 8.1 over sine of 72 degrees. So C sub 2 equals to 8.1 times sine of gamma sub 2 over sine of 72 degrees. Typing all into your calculator, you have approximately 0.749 meters. Okay, so with the given information, right, we know side A, B, and alpha, angle alpha for both of these triangles. And then we found the approximation, well, the exact and the approximation for angle beta in both triangles. And the approximation for gamma in both triangles. And the approximation for side C in both triangles. And the exact values. Okay, and then let's look at this last. Now, the given angle is 107 degrees. So, you know, there's potentially only one triangle. I will never on a test give you a question where there's no triangle. But I want to show you what happens when there is no triangle. So, I'm kind of giving that away, but I want you to see what that looks like. I know my picture isn't accurate, but I just like to organize or give myself a visual of what I have. Okay, so we would need to try and solve for angle beta here first. So we would have sine of beta over 8 equals 2 sine of 107 degrees over 6. And then multiplying by 8 on each side of the equation, we'd have beta equals to inverse sine, of that ratio. Now, if you type that into your calculator, you get an error message. And that's because this ratio is greater than 1. Okay, and if you think about the unit circle, right, the largest value of sine and cosine too, the largest value of sine is 1, and the smallest value is -1. Never goes above 1 or below -1. We'll talk about that more as we study the graphs of the trig functions, and we talk about the inverse trig functions more in depth. But we get this error message. This means there is no triangle. Therefore, no triangle exists with this given information. Okay, again, on a test, I would not give you information that did not represent an actual triangle. Okay, make sure that you are storing values in your calculator. You are representing exact values on your page, even if you're having to use the variables to represent